Okay, let's talk a bit about the electric force. Before we get into that, though, we really need to talk about this idea of electric charge. Electric charge is going to be kind of like mass. It's a property of matter that it can have, and it's going to be a little more exciting, though. Right off the bat, we've got two varieties of electric charge. We're going to have positive charges and negative charges. We'll spend some time in lab kind of playing with this idea and seeing where it comes from, but for now, let's just take this as a given and roll out with it. So you might be wondering, what happens? I've got a positive charge and a negative charge hanging out nearby. Are they going to interact? Do they see each other, ignore each other? Well, we know whenever two masses are nearby, gravitationally, they get attracted to each other. That was the whole idea behind gravity, in case you forgot. Charge, though, is a little different. With charges, we care about the sign of charge. That's going to tell us how this interaction works. So if we have a positive charge and a negative charge, they are going to be attracted to each other. If, however, I have a positive charge and another positive charge, they are instead going to be repelled by each other. To sum this up, I kind of like to think of something called the law of romantic comedy. The law of romantic comedy, that's probably how you spell comedy, basically says opposites attract. It also implies at least the converse of that, and that is that likes repel. So that's going to be kind of kicking around in the back of our head when we're looking at charges. This is going to tell us the direction of the charge, at least. The direction of the force, sorry. If I've got like charges, I know that they're going to be pushed away from each other. If I've got unlike charges, I know they're going to be attracted to each other. Now, there's a full-on physical law for this, and this is going to be Coulomb's law. We're not going to get too into this, but let me show it to you just so you have a frame of reference. We can think about it. And this is going to be a model for an electric force. So there's going to be some constant K, which in some books will look like this. It'll be 1 over 4 pi epsilon naught. But as you can see, that looks scarier than K, so we're just going to go with K. K is just a number. It helps us get the units right. We're not going to worry about it. It's going to look like Q1 times Q2 over R squared. Now, as you no doubt are aware, when I write Q, Q is going to be our symbol for charge, because, you can't spell charge without apparently using a Q. R, in this case, is going to be our separation. So what this tells me is not that we're going to worry about the form of this. It's a 1 over R squared law, and that will matter later in your life. For now, all we need to worry about is that if I look at the top of this thing, I see that if there is more charge, I'm going to have more force. If I look at the bottom of this thing, I see that if my charges are closer together, I am also going to have more force. And so that's what we want to keep in mind. If my charges are bigger, the force between them is stronger. If my charges are closer, the force between them is stronger, and then the opposite also applies. Further out, smaller force. This is going to help us as we look at situations and we want to figure out, all right, if I got 3 charges, does that charge in the middle want to go to the left or to the right? Well, we can think, if I've got a charge chilling out here, some 1 Coulomb charge hanging out next to a 2 Coulomb charge, hanging out next to a 3 Coulomb charge, just kind of hanging out, doing their chargy old things. I can ask a question, what will this charge in the middle do? That's a fair question to ask. And now we know it's going to be repelled by both of these. Apparently it's a snooty charge, I don't know. But it's more repelled by the 3 Coulomb one. So if I were to draw a good old-fashioned 3-body diagram, here is, my 2 Coulomb charge. Here is the force on 2 by 3. It's a big repulsion. Here is the force on 2 by 1. It's a small repulsion. So it winds up going to the right. Easy enough. Assuming these are the same distance at least. We'll see some other examples like this on the homework and you can, work it out there. Now, the other thing we want to talk about a bit is charges in matter. Because if it's not matter, well, it doesn't matter, at least for us. And so in this case, we're going to have 2 big categories of matter. We can say everything in matter is either a conductor or it is an insulator. And so when we think about this, a conductor That's not the right color of ink, sorry. A conductor is going to be something that allows charge to move freely. Big examples of conductors are going to be metals, people, water, assuming that it hasn't been deionized or something. These are things that basically, if you put a charge near them, the charge is inside of the material. They're going to be free to wiggle around and move and rearrange to adapt. Now, in an insulator, you have the opposite, basically. Charges are not allowed to move freely. And when we think of insulators, we're going to think kind of, maybe wood, plastics, stone. There are degrees of this, and then you can get things like superconductors, which are conductors that wear capes, and semiconductors, which are conductors that have had a tragic accident in their past and been cut in half. It's not true, by the way, either of those definitions. But for now, we're really just worrying about conductors and insulators. And the way we can think about this is, imagine a situation where you have a parent who is with a small child. You can tell it's a small child because it has one of those tiny hair things on the top of their head. And now this parent has taken the small child to a mall, a dangerous choice. But the parent has elected to use one of those little backpack things that maybe looks like an animal, but is really basically a leash. Now, two cases, right? Conductors and insulators. If it is an insulator, then when the kid, for example, sees a toy store, then the kid wants to run to the toy store, as children do. And kid is trying, but the kid is ultimately on a leash. And so the leash extends a bit, and the kid gets a little bit towards the toy store, but ultimately, the kid doesn't get there. Basically, what we wind up with, we get a local rearrangement. So in this case, here's our atom, basically. These are our charges. So the kid, let's say the kid is a negative charge, and the toy store is this massive positive charge. The kid is like, I want that. But because we have an insulating parent-child thing, I guess, go with it, the kid can only go so far towards the toy store. Now in our conducting case, we again have our toy store, which is full of positive toy goodness. And we have our kid, who is full of, I guess, negative toy goodness. Don't go too deep into why the kid is negative and the toy store is positive. We're not saying this kid had some horrible history and has, been traumatized or anything. But in this case, that wonderful backpack that's so cute and stuff, it broke. And so this kid can go flailing on all the way over to the toy store and smush their face up against the glass and just kind of drool on toys to their heart's content. And this is what happens this is going to be our conducting case. In this case, in a conductor, the charge, our kid, can rearrange themselves to the extent that they physically can. They can run as far as they can. So they can run right up to the glass of that toy store and smush their face against that glass, and it'll be all adorable to everyone who's watching, and the mother or father there's just like, oh dear God, why today? Why today? But kid attracted to the big external positive toy store. Here, still a big gap between them. Kid can only get so far because of leash. Insulator, conductor. You may think this is a ridiculous example, and I mean it kind of is, but it holds up much better than you would expect. So we'll do some examples talking about this in class, and we want to think of what happens when you have a chunk of matter instead of a kid with a animal backpack. And we're going to kind of always fall back on this idea of Coulomb's law and this law of romantic comedy to guide what's happening here. How our charges are responding to other charges around them. And so this will be our starting point for this unit. So, get excited. It's going to be, well, Now it's going to be fun. I'm not going to make the pun. See you guys later.